Okay. All right. So, by the way, has anyone started the chapter 1 homework?
No, I will be.
Please tell me if it's at least doable this time, because, like I said, every previous semester it's been an absolute train wreck.
Is that the one? Is that homework 5 or 6?
It's 6. 6.
Okay, no, I have not started.
All right. So we've actually been cruising through this book. We got one chapter left. We may actually get through it today. There's no class on Wednesday, if I haven't told you already.
What? No class on Wednesday.
No class
Why?
Wednesday.
He's going on spring break.
Yeah, I'm going spring break.
Oh, because your kids are off, right?
Yeah.
Yeah.
So.
That's reasonable.
Yeah.
Yay, nothing to do on Wednesday. I don't have to do chapel anymore. I don't have class. Is great.
Is there even chapel on Wednesday?
I don't know. I'm just being
Did
excited.
sleep in? I don't think there is
Yes,
this
I think
week.
so.
Is
I think
there?
it's the choir.
Are you serious?
I have 48 credits. I don't need
All your
everyone.
classes getting canceled too?
My only class,
Yeah,
I
it
have
is.
one class
Yeah,
Monday through Thursday
that's
and none on Fridays.
Yeah.
And my only Thursday class has already been canceled too.
Wow.
So I have a Wednesday through Sunday on a weekend.
Nice. Just take a mini vacation.
Just go somewhere, have some fun.
Get caught up on homework?
Well, my
Sorry. Go ahead.
dog is down here for the week with me, so I'm just
Okay.
gonna spend all my time with him.
Okay.
Just bring him to class.
All of it, like
Bring
24 hours a day.
I almost had to bring him to class because he didn't want to be left.
You should.
Shut
You should.
up.
It would not bother me. I don't know what CSU's policy is though.
Probably not favorable to the dog.
Yeah, probably not.
Actually,
Just
I had
bring
a
him
psychology class where the
downstairs.
psychology teacher had a dog in the classroom one day.
Just bring him
so.
downstairs and we'll go all hang out down there.
All right, so okay. So I think we're pretty close to the end. We just need to do our homework with this chapter, and then everything else I've assigned, and that's gonna
Yeah.
actually be it. And then the final, of course,
So we
the
just
final.
come in for
Wow.
help, basically.
Yeah. Well, I still need to present on MPI OpenCL,
Yeah.
and then we're gonna do a review, which
Yeah.
we'll do on that Monday, and then wrap it up.
That's nice.
You're welcome. See, I front load my classes, don't I?
Yep.
Yeah, I mean it makes
That's true.
me very stressed out very quickly. But at the end it's great because while I'm getting stressed out from all my other classes, this class is like
We're done.
chilling, and it'll give me time to
Study.
look over all the videos.
Okay, so today we're going to talk about parallel processing. What I've hopefully shown you, at least somewhat, is that we've tried to exploit instruction level parallelism, where we try and run multiple instructions at the same time with pipelining. What I'm going to talk about next, I haven't talked about SIMD, have I? So, there's a lot of other techniques, that's good because we'll be talking about today, in order to improve performance or more parallelism inside of processors. A lot of this is a little outside the scope of an introductory computer architecture class, but we need to at least cover some of the basic concepts because you should be aware of them while you're coding. And there's a whole slew of different techniques we've tried to employ for parallel processing, all with varying levels of success. Unfortunately, most of them are difficult. Yep. Really, the pipelining has been the best one, and now everything else is just not as good. But it's still very useful.
At least we tried.
Hey, well, we got, people want faster processors, right? And companies are there to make money, so we've got to do something. Good old capitalism. All right. So there's different ways to do it. Okay, first goal, connecting multiple computers to get higher performance, or at least multiple computing units is actually a better way to do it. Not necessarily multiple computers, but different, even at the basic level, multiple ALUs, connect them together somehow so that they can compute. And there's different levels here, because you can do task level, where you have different computers running on something. Parallel processing, you have one program running on different cores inside your machine, and then chips with multiple processing. Did we talk about data here? There's data level, which we are going to get into, where you have basically a CPU with a ton of ALUs, and they're going to have an instruction that tries to utilize all of them at the same time.
That sounds like a mess.
Oh, it gets complicated. So, your hardware. Yeah, nowadays we pretty much always have parallel hardware. Back in, I guess, around early 2000s, where the switch was, everything was serial. Pentium 4 was definitely a single core machine, but nowadays, well, quad core Xeon, but even our phones are at least dual core. I think most of them are quad core now.
There's 8 now and some.
Yeah, 8 of them, and then your desktops, of course. This one's at least dual core, and it's got hyper threading, so
I think
it
mine's a quad core.
looks like 4. Yeah, we'll talk about that as well. So sequential concurrent software can run on both types of hardware, but the problem is making it effective use of parallel hardware, which is actually very difficult. So we've talked about parallelism and instructions. I hope we have. And this was with your pipelining, pipelining. We haven't talked too much about parallelism in computer architecture, so sub-word parallelism. We're going to get a little more into that. Chapter 4 is where we talked about more pipelining, and then parallelism and memory hierarchies. We did not go into cache coherence. Well, wait, did we? Yeah, we did.
Yeah.
Yeah, we talked about cache coherency. Great. But we're going to focus more on the individual computing unit here. So parallel programming is the problem. What's going on, this is the issue. If you remember that last graph where we were talking about, we were getting about 52% performance boost every year, and then all of a sudden it was back to 22. The reason for that, here's the issue, is that during that 52, aka the golden era, so to speak, we just had a sequential processor, and we just made it faster and faster and faster and faster. And we were able to do that by increasing the clock rate. Bless you.
Thank you.
Not a problem. Significantly every year to get that 52% boost. Unfortunately, once we hit that power wall where we can't reduce or remove enough heat anymore to improve the clock cycle, we're having to find other ways in order to improve performance. And hardware manufacturers, Intel, AMD, all the big ones, they're basically saying you have to go to parallel programming, which is not anything new. People have been doing this since the 60s and 70s. We want significant performance improvement. If we could just use a faster sequential processor, we would, because sequential code is way easier to write than parallel code. But unfortunately, we've just hit the wall, and the hardware people, we're just saying it's now a software problem. Well, we'll give you the hardware, but it's your problem now. The issue is, if you're trying to do a parallel program, you need to partition it into different chunks. Who's going to work on what? How do you coordinate them? You don't want someone overriding or stepping on each other's toes while they're trying to work. And then, of course, communication overhead. One way to think about this is you're trying to build a house. You can have a bricklayer and an electrician, and they could technically be working at the same time, unless, of course, you needed the electrician to be finished before you laid bricks, or vice versa. Then you have coordination issues as well. You don't want them working on the same spot. Again, coordination. Also, they need to be able to communicate to each other, so they have to talk to one another and set things up. That's an overhead as well, because that's them talking about setting it up and not actually getting work done. Does that analogy make some sense?
Yeah.
Yeah, okay. Amdahl's law. So yeah, the sequential part can limit the speed up. Hopefully, when if you're thinking about this with like building a house, there's some parts that have to be done sequentially before you can get to other parts. But for example, let's think of it more concretely. If you have 100 processors and you want a 90x speed up over a single processor, let's say you have one processor and you want to have it be 90 times faster when you boost it from 1 to 100. First off, is that possible? Well, is it possible? Like if there was no issues with communications and whatnot, theoretically you should be able to get about 100% performance, 100 factor speed up. Theoretically. So 90, okay, that's within the realm of possibility, but let's see what it comes out to. So you want your new speed up time. Basically, you want everything that's parallelizable divided by 100 processors plus your sequential. What this is saying is there's some time in your program that's sequential. You can't do anything to parallelize it, but there's some parts that you can. That part you can. You want to divide it by 100. If you basically math it out, you find out that the parallelizable part needs to be 99.9%, aka sequential part needs to be 0.1%. The point here is that it's not very intuitive how much needs to be sequential or parallelizable in order to get the speed up you want. Okay. All right, what are we doing? Wow, we're just doing through a lot of workload example. All right.
Math is okay.
Math's okay? You okay with it? So what are they doing? I think this one they're trying to show you what speed up you get. Oh, okay. what we're trying to show here is that adding more processors does not necessarily give you a linear speed up that you may be expecting. For example, you have 10 scalars, aka 10 by 10 matrix sum. You want to know what's the speed up from 10 to 100 processors? Okay. Well, a single processor is 10, aka your 10 scalars, and you got 100 10 by 10 matrix, 100 units times however long it takes to add. So in your 10 processors, when you're trying to do each 10 of them, you got 10, 100, 10 by 10 equals 20, that's right. Yeah, you can only parallelize this part is what they're trying to say with your matrix as opposed to your scalar, because when you do the scalar, it's just one unit. You can't really do different parts of that matrix. So they're saying it's a 55% potential speed up, but if you had 100 processors, since that sequential part's still sequential, it's only 10% of potential. Naturally, you're assuming the loads can be balanced well across processors, which is not going to happen.
You can try.
You can try. But if your matrix was 100 by 100, notice what happens when you do the math. You get a 90. You get a basically a speed up of 9.9 off of 10 and 91 off of 100. The point here, notice that in this one the parallelizable part was significantly bigger, but on this one it was significantly less. Hopefully this is intuitive, right? Yeah, if your parallelizable part is not much of the whole problem, you're not going to get much of a speed up from adding processors. Okay, strong versus weak, fine. Strong scaling, the problem size is fixed, aka you know exactly how much of it can be parallelizable. Let's see, weak scaling, the problem size is proportional to the number of processors. I don't really care about this definition. Let's go to something that's important. Here we go, finally. Okay, this is called, was it Flynn's taxonomy? All right, this one's important. Let's stare at this for a moment. This table is to help you understand different types of parallelism or different types of machines. The ones we've been talking about so far is you have a single data stream and a single instruction stream. This is with our single cycle processor, our pipeline, and our 5-stage in-order pipelining processor. You have one instruction, you get one piece of data, you move on, right? You're in a constant get one piece of data, so forth and so on. The big next one is called SIMD, where you have still a single instruction, multiple data. So over here, you might load one word into your register file. Here you might load multiple words excuse me, into your register file. Here you might add basically two numbers together. You know, you just do one add. Over here you might do 4 adds or 8 adds or 16 adds in one instruction. The point is that you can do more adds with a SIMD than with a single cycle. This one, you still have essentially one processor, but you're able to have multiple ALUs and do all the adds in parallel. We're going to skip this one right now because it actually doesn't make too much sense. MIMD, multiple instruction, multiple data, that's if you have multiple cores running around and you're working on multiple pieces of data. So multiple instruction streams, multiple cores, and multiple pieces of data. They each have their own data to work on. Bless you.
Thank you.
Does this taxonomy make some sense? You're going to see this again, like on your final.
Yeah.
And by like, I mean definitely on.
Hint, hint. Nudge, nudge.
No, that's not a hint. That's just straight up. This is.
This is. I'm just telling you how it is. Okay. Let's do an assembly example. I'm sure Caitlin can't wait to explain this.
I don't mind assembly.
You don't? Oh, good.
I just don't like the rest of it. I don't like, the one thing I don't like of assembly, floating points.
Floating points? Okay.
The rest
Well,
of it's fine.
unfortunately, we can't help that.
Yeah, floating points are weird.
All right. So we're adding double add and what, product? Yeah. So it looks like what we're doing, we're multiplying a scalar by everything inside of a vector and then adding it back to the vector. Okay, so we load the scalar, the upper bound of what you need to load an x sub I. Great, multiply it, load a y, add it, and store it back out, increment your x and y, compute the bound, and then branch if you're done back up to here. You're going to load the next I, multiply it by a, load y, add it, and then store it back out, increment again, and then go back out. All right, great. So what they're trying to show here is that when you're multiplying, notice that, what do we got? F2, where's F2? F2 is the x, so it's being multiplied there and then added later on. What type of hazard would that be?
You're using it later on. So that would be the, I know with pipelining it would be the one issue where it's not done yet.
Yeah, so read after write.
Yeah, that one.
Multiply is going to take longer than one cycle. A load might be in there in the middle, and then the add, so there's a issue right here. There is technically an issue with the writing, but we haven't gotten to that yet. Well, you'll get to that if you take advanced. Wow, that's didn't tell me anything more.
Awesome.
So the vector version of this, think about this. Notice here we have a loop. On your vector version, you load A, you load the vector. Notice it's loading a whole vector. It's actually just loading at least a part of it into memory. And then it's going to do the multiply. Look at that. That's one instruction doing the vector multiply, that section. And you're going to load the entire vector y and then do the add and then store it out.
Wow.
What just got eliminated?
Half of it.
Well, half of it, right? More importantly, what got eliminated?
The issue. The warning.
The warning.
With the F2.
Okay, sure. Yeah, we got rid of the hazard, which was great. So we got rid of the hazard, which was what I actually harped on. But there's another thing that we got eliminated that is very important.
The loop.
The loop. We're no longer looping. We don't have to add some incrementers and then do a check. Remember with the branching, what's a big problem with branching?
You have to check stuff.
Yeah, check stuff, and if you're wrong,
Well, you're in trouble.
you're in trouble.
Yeah.
What happens?
You can go in an infinite loop.
Sadness. Well, you can go in an infinite loop with
And
it.
then
That's
crash
true.
your whole
What happens on the processor if you mispredict?
Mine almost did.
Just did this last time, guys. If you mispredict a branch, what happens to your pipeline?
Doesn't work.
No, you can still make it work, but what do you have to do?
Make it the exceptions.
Exception stuff? No.
Yeah, it's been a long weekend.
Anyone?
I mean, it's like everything like basically just like stops, right? So you
Stops, and then, but what do you have to do? Because you're pipelining, so you had a bunch of instructions you were executing, and then you mispredicted the branch. What
Oh,
happens?
you gotta get rid of all of it.
You got to get rid of all those instructions. Did you just waste a bunch of computing time?
Yep.
Yes. Can that happen down here? No, because there's no branch. So you know exactly what's happening. So we've eliminated multiple adds and a subtract, which is really just another add and a branch. And we've not just eliminated 4 instructions, it's 4 times however long this vector is. So we've actually eliminated a lot of unnecessary work, which is why these instructions can speed it up.
I feel like there's
No.
a butt coming in. There's going to be some issue with this.
Okay. Yes, but hang on. Notice also, this one's a little harder to see, but up here you're doing multiply, add, and then doing the next multiply and add. Down here you can go and do all your multiplies in parallel, because it's one instruction, right? You don't have to do them sequentially. You can do all those multiplies in parallel, do all your loads in parallel, do all your adds in parallel, and then store it back out in parallel. So instead of up here forces you to do it sequentially, down here you can do it, the hardware can do it in parallel, which is a significant boost. This is another SIMD, single instruction. It's just one instruction, but it's operating over multiple pieces of data. This is still considered SISD. I mean, yes, you have 2 pieces of data, but you're really just storing it back out to one location, which is why it's a single data stream. All right, so what this is called is a vector machine. You can think of it as you're loading in the vector or the array, and you're able to operate on an entire vector. So this is a vector processor. One example just show you was the extension to MIPS. You could have 32 64 element registers. So that's 30. Your vector can be 32 elements wide. You're going to be able to operate on the entire vector. Load vector, store vector, add vector. What was that? Add. Add scalar to each element of the vector. Sure.
Something else.
Significantly reduces instruction fetch bandwidth. Anyone want to guess what that means?
Oh, that's the getting of stuff.
Of the
Instruction.
instruction. Why is the bandwidth lower when you?
Because you only have to get it once.
Yeah, you only have to get the instruction once.
Instead of every
You just
time
have to load these instructions as opposed to all of these.
Yeah.
Another huge benefit as well. All right, vector machines compilers. Nice thing about vector and SIMD is it's a very simple data parallel programming. Your compiler sometimes can go and figure out, hey, we're just looping and doing these simple adds and multiplies. Maybe I can automatically use these vector instructions. Yeah.
They're smart.
Yeah, that is really hard to do, by the way, but compilers can do it. You actually avoid the control hazards with loops. We talked about that. More general, the ad hoc media extensions. All right, we haven't talked about MMX and SSE. Have you all seen those two before?
No.
You haven't seen SSE before?
Maybe not
That
with
looks
a name.
familiar.
Yeah, they're different. Here we go. What's
You guys- I think it's right out.
CPU info? It should be in here. Here it is. I got SSE and SSE2.
Oh, and
Yeah.
MMX.
And MMX, great. What am I looking at here? Oh, well, these are the different extensions to the standard x86 that my processor has. By the way, why are there so many of them?
Kaiser.
That's good. Well, Kaiser's what stops you from having Spectre and meltdown issues.
Fun.
Yeah, but you got to implement other things as well, fortunately. But that's okay. Why are there so many of them? Well, I mean, this process has been around. The design of the processor started in 74, 75.
They
So
just keep adding
they
stuff
just
on
keep
them.
adding stuff on
I
top.
love the fact that like some of them are like actually it makes sense. Like these are actual words, and then others are just like here's all these letters. Here you go.
They're acronyms.
Well, I figured, but still, it's just like here's a mess.
Floating point unit was the first big one. Oh yeah, we can do floating point now.
There's like shadow.
Wow, look, it identifies which bugs I have.
Oh.
Thanks. We'll just put that on YouTube, no problem. Now I'll just post my IP address and I'll be good to go, right?
Right.
Oh well. All right, more general ad hoc, better match with compiler technology. What it's saying is if you have a fully vector architecture, it's actually simpler than MMX and SSE, although MMX and SSE can still give you some good boosts as well. All right. Let's see if I can say this correctly. A vector machine is an example of a SIMD implementation. There are many different SIMD implementations, aka single instruction, multiple data. MMX and SSE are on x86, multiple data elements, 128. Let's see if it tells you. Please give me the example. It does not. Okay, great.
Nice.
Let's do a simple example. I thought I did this once in this class, but maybe it was somewhere else. All right. When you're working in pixels, what is stored in the pixel?
Data.
What data? How do you do colors?
It's the lots of numbers. There's
It is
six,
numbers.
It's like six numbers.
Yeah,
It's hex.
'cause there's
It's
like
text, but how's it split up? Yeah, each element.
It's like
Three
it's like
sets of two.
RGB and
Right,
each
so you have red.
There's a
Green.
2-digit hex value for red, green, and blue each.
That's
Yeah.
right. There is one more in general.
Oh yeah, because there's like an alpha channel.
Now the alpha one is optional,
Yeah.
Yeah.
and also it doesn't have to be this way. But you said it was two
It's
hex.
Yeah, it's a
two
2-digit
per-
hex.
So how many bits is that?
So let's see.
2 digits
A hex is
32.
as in nibble, which is 4 bits. Did y'all know that nibble is 4 bits?
is. Nope.
Alright.
Never heard of a nibble. At least not in this
And a byte. But you know what a byte
Because
is.
it's a
get
little.
it.
Okay.
Get
Who
it.
came up with that?
A very smart person.
So it's 8 for red, 8 for green, 8 for blue,
Yep.
and then 4 for alpha or 8 for
It is actually 8 for alpha as well. So how many bits are there per, I'll say an expanded or pixel? 32. Great. Now, if there's, well, you have 4 different 8s. If you wanted to add them, what would you have to do with our standard instructions? You would have to, in your standard instructions, you'd have to load this into a register, him into a register, him into a register, him into a register, add those individual registers, and then paste them back together using some shifts and bitwise, and then load it, store it back out. Not the most simple thing, best thing to do. But if you had a single, because what if you wanted to add 1 pixel to another pixel? Well, that's what MMX and SSC were doing. Is all right. We'll just pretend that you're doing 4 8-bit adds, and we'll store it back into a single register. Ta-da!
Magic.
Right?
Yeah.
But that is SIMD because you're having 4 different elements. Granted, they're only 8 bits, but you have 4 different elements, and that actually significantly improves performance. Hopefully a good concrete example of SIMD or MMX and SSE.
We should do some pixel art.
Pixel art? Okay.
That'd be fun.
Everyone got that? You got this?
Yeah.
Simplify synchronization because you just have one instruction to do all those adds. You don't have to synchronize it afterwards. Reduced instruction control because you don't have to break apart that pixel into different registers, add them, and put them back together. It's just one. Works better for highly data parallel applications. Right. I mean, this is because you're operating a lot of different data, and there's many pixels on the screen, so there's a lot of parallelism here. All right, let me take a break.